test your algebra ability. This is a very, very reduced version of yesterday's test. If the second derivative with respect to x of a function is greater than 0 and the d value, which we know, I'll write it down in more detail, is positive. So if they're both positive, you're looking at local. Excuse me, I don't know where that came from. Stupid asthma. And then you have the second derivative is less than 0, but d is still positive, then you've got a local max. And you don't really care what that is, but if d is negative, you've got a saddle point. And we do these checks on the critical numbers, and the critical numbers are the places where the first derivative with respect to x and with respect to y are both 0, and that's where the heavy algebra can start. So first thing I'm going to do is find these critical numbers for this question. So if you find the partial derivative of this expression with respect to x, you get y, that gets you nothing, minus 3, that gets you nothing, and negative 2x, and that gets you nothing. Double check. With respect to x, yeah, with respect to x, nothing at all. With respect to x, none at all. Okay, and that's going to be 0. I mean, if you do a partial derivative with respect to y now, that gets you x, that gets you nothing, that gets you negative 3, that gets you nothing, and that gets you negative 2y, and you have that. In this particular combination, since both equations, I'll call them 1 and 2, since both equations contain x's and y's, isn't that just a system of equations that you've learned to solve way back in Math 94 and 99? So that one here actually came out a lot nicer than I thought. And what I would probably do is I take equation 1 and I'd rearrange it by adding 2x and adding 3 to both sides. So that's equation 1, rewritten in that way. I can then put this guy into equation 2. And if I do that, I have an x, take away a 3, take away 2 lots of y, which is now replaced by that guy, and it's equal to 0. So x, take away 3, minus 2 y's. And at this point onwards, it's as long as I don't screw up, which is very possible. I can just go through the usual mechanics. And I believe the answer is negative 3. Does that look good? Okay, I need to know the y coordinate then. Can't I just plug negative 3 into here? And we got it. So we have only one critical number, and that happens to be at the point negative 3, negative 3. So what we now need to do is we need to find the second derivative with respect to x, and we also need to find d. Well, here is the partial derivative with respect to x again. I need to know the second derivative with respect to x, which happens to be a number again. We know y, which is this guy. And I need to know the second derivative again with respect to y, and we get that. And I also need to know f of xy. So I guess I could do this one, and then partial derivative with respect to y, and I get 1. And that allows me to get d, which is this guy times this guy, take away this guy squared. This fellow happens to be negative 2, so does this guy. And this guy happens, I'm getting deja vu here. Like I've done this one before, but too late now. Okay, we got this guy here. We're ready to do our test. We only have to do it at one point. There's only one critical number here. And we are going to be looking for whether it's local max and min. Well, the second derivative is negative 2, which is that guy. And d is 3, which is positive. And so Second derivative with respect to x is negative and d is positive. We have a local maximum at the point -3, -3. In fact, I think if you put that shape, it ends up looking like that, and we've just found that guy there. Are we comfortable with the process? I kind of zoomed through that because it ended up being a lot easier than I thought it was going to be. How you go looking for and finding local max and mins or saddle points. Are we good with that one? Okay, I got a whole list of them here, so I'll see how the next one's going to work out. This is like question 6. So let's find the critical numbers. Partial derivative with respect to x is going to be 6x squared take away 6 plus 6y squared, and that's going to be 0. And the partial derivative with respect to y is going to be nothing, nothing, and 12xy. And that's going to equal 0. So that's going to be equation 1, and this is going to be equation 2. That one there's got too much going on. I don't want to focus on that one. This one here is much easier. Would you agree that there are 2 possible ways in which this expression could be 0? And since critical numbers, both things must be true, I only need to worry about what's true here and see which ones it matches. So if you take this expression, would you agree x could be 0? And the other possibility, and the only other possibility, is y equals 0. Now, if x equals 0 and I plug it into here, right, I will get 6 lots of nothing squared, which is nothing. I will get -6 plus 6y squared equals 0. And since I don't have a lot of room, can I tell you that the answer to that is plus or minus 1? And if I plug y equals 0 into here, I get 6x squared take away 6 is 0. And that comes out to be plus or minus 1 as well. So we have critical numbers. X is 0, y is 1. X is 0, y is -1. Y is 0, x is 1. Y is 0, x is -1. Do you see that there are actually 4 critical numbers here? Okay, let's pause at that. Are you comfortable with how I found the critical numbers for this particular function? You're comfortable why there are 4 choices? And you could double check them. You take any one of those 4, and I bet if you plug the x and y into here, you get 0. And I bet you if you plug the x and y into here, you'd also get 0. And that's what we're looking for, right? Places where both those partial derivatives are 0 at the same time. Are we good? Right. So now we have to do all those different partial derivatives so we can do the test. So here is f of x. I'm calling f of x, the partial derivative, f little x. That's that one. If you do its second derivative with respect to x, you get that. If you do xy, what you're going to get 12y. We know f of y, it's 12xy. And if you do f of yy, it's going to be differentiating without, you get 12x. So that's all the pieces, I believe. D is f of xx times f of yy, take away f of xy squared. This guy is 12x, this guy is 12y, and this guy here, oops, this guy is 12x, this guy is also 12x. Take away f of xy, which is this guy, squared. So that looks like 144x squared, take away 144y squared. Does that look good? You know I make mistakes. Does that look good, guys?
Yeah, but can we just call it 144 times x squared minus y squared?
I probably would. because it looks pretty anyway, doesn't it? And for evaluation, that might be a little bit quicker. We have 4 critical numbers to test. 0, 1, 0, -1, 1, 0, and -1, 0. Now, any one of those could be a local max, a local min, or a saddle point, right? I guess you could have 4 saddle points. Anything could happen. But we have to check each one to decide what it's going to be. I don't want to do 4 of them because it takes up too much time. Which one of those 4 do you want me to test, just to show you how you would test them? 1, 2, 3, or 4. Which one do you want?
1.
Okay, we're going to test that one. So that's x equals 0, y equals 1, right? Now, the second partial derivative with respect to x is 12 times 0, which is just 0. D is 144 x squared take away y squared, which ends up being negative 144. Isn't that guy negative? If D is negative, what of the 3 possible things are we looking at? Local max, local min, or a saddle point? What do we have here?
This would be a saddle point.
That is a saddle point. Were you a little bit worried about the second derivative with respect to x being 0? Right, because our test doesn't mention what happens if it's 0, but thankfully it was a saddle point, right? You see our test, it has to be bigger than or less than or equal to, but that is a saddle point. So there's your answer. And I believe when you do the answers, you put the coordinates of the saddle point down. But when you do max and min, you actually put the value of the function at that point. So you might say the local maximum is 42, but the saddle point is 0,1. So bear that in mind when you're writing your answers down, right? That when they do saddle points, they expect you to write the coordinates down. But when you're doing local max and min, they want you to put the value of the function, right? The original value of the function. So local max at 42 kind of thing. Are we good with that? I'm not going to do all 3 of them, but it'd be the same process. Side issue, because I just thought of it. And I'm pretty sure it won't happen because it would make writing down your answers quite difficult. But can you imagine a situation where this did happen? Sorry. Write it again. What conclusion would you be able to make, if any, if the second derivative with respect to x was 0 and d was also greater than 0 at that point? Could you make any speculation on local max, min, or saddle point? Ethan. Say again, Sally?
No. Just because to be able to determine if it's a local minimum or a local maximum, it has to be either greater than or less than 0.
So that is an example of what we would say it's inconclusive, right? We don't know. I mean, if you wanted to know, wouldn't you just put it into GeoBra and look at it and say, oh, it's a hill or whatever? Because it could be a hill, you know, local min, could be a local max. How about this situation? D could be 0, right? With certain combinations, can you imagine D could be 0? That is also inconclusive. So none of them should happen. The reason I'm saying none of them should happen is that none of the homework questions has a box that says inconclusive, right? So you hit that one when it happens, right? So since all the answers are local max, local min, and saddle point, I'm convinced that these 2 are not being treated, right? They're not just pretending they couldn't happen, right? So you're not going to see those. But will you be aware they could happen in real life? So can you imagine you're doing your own math question and you're thinking, oh God, what does that mean? Well, it means you don't know, right? So it's inconclusive. You probably want to look at the picture to make up your mind, right? And that is that guy. And the reason that came to my mind was that happened, didn't it? You know, we got one of these and we thought, oh, okay. Here's our next one. Let's go for critical numbers again. Partial derivative with respect to x. 3x squared, don't get nothing. Minus 6x, don't get nothing. Minus 9 equals 0. Partial derivative with respect to y. 3y squared, take away 18y. Equals nothing. Double check that. Yep, nothing. That. Okay, now we are looking for critical numbers. Places where this is 0 and at the same time this is 0. If I take this guy and I pull out a 3, we get that. If I then factor, we get that. So doesn't that give me an x is 3, and another possibility would be x is -1. Do you notice that that particular one didn't have any y's attached to it? So algebraically, didn't that make that a lot easier to deal with? Now, if we take the partial derivative with respect to y now, which is this guy, I can pull out 3y as a common factor, and I believe I get this. And that generates y equals 0 and y equals 6. So how many critical numbers will you get from this story? Do you get 2? Do you get 4? How many different ones do you get?
4.
So you get a 3 with a 0, a 3 with a 6, a -1 with a 0, and a -1 with a 6. And that's where I want to finish this question. Wouldn't this pretty much be a bread and butter question now? Wouldn't you find f of xx, f of fy, all the stuff that you need, and calculate d, and then you would just simply pick a point like this one, find out if f of xx is positive or negative, find out whether d is positive or negative, and then you can decide which one of those 3 it's going to be, because it is going to be one of those 3 things, right? Is it okay for me just to leave it at that point? Because we've got a lot to do. Okay, that's 7 done. This one's a little bit different. It has some constraints on it. All that means is that there are certain restrictions or constraints on what x and y are allowed to be. Can you imagine in this question, because it contains trig functions, wouldn't this be an infinite number of hills and valleys? So you don't want to have to write down an infinite number of answers. So they are saying x must be in this range and y must be in that range. So that's same story. Question.
Got a request.
Right, I can't hear it. See it. What does it ask?
It's Joel. It's an odd request.
Yes.
You know that window. You know that window that you appear in.
Yes.
Can you move that to the opposite corner?
Where is it right now for you?
Oh my God, that's so perfect. Yes.
So here's the thing, on the playback, it always is in the right upper corner and it obscures some of the stuff that you write down.
Good
yeah, so like it'll
idea.
obscure the
Right.
constraints.
I've moved my camera to make this side black. Am I now in top of a black bit and you can see the paper?
It's way better.
Yeah, that's way better.
Okay, I can do that. I'm going to have to move, not that you need to worry about, I'm going to have to move the window with your pictures on it because now it's distracting what I can see. Okay, we're good. So let's go hunting for critical numbers. The partial derivative with respect to x. If you differentiate this thing with respect to x, you will get 8 cosine x sine y, and that has to be 0. And if you do it with y, you get 8 sine x cosine y equals 0. Are you comfortable with what we just wrote down there? Right, now I'll start with the first one, right? This guy being 0. cosine x can be 0 at what values of x, and sine y can be 0 at what values of y. So let's do the cosine x. What values of x do you get a 0 for the cosine?
That would be pi halves and 3 pi halves.
Right. That's the only one I'm going to use because you see the restriction stops the other ones from working. Can you get negative x's? Is there a negative x that would also give you 0?
3 pi halves is also called negative pi halves.
Okay, so that's the two that I'm going to use because they live in that range. Are you comfortable how I got those two guys? Right. Now, what about the sine of y? For what values of y do you get zeros? So what value of y is the sine of y 0?
0 and 2 pi.
And also pi, but none of them are going to get used because they're outside the range. Are we comfortable about those combinations? Right. Now, I'm going to then move on to this combination. So as long as I make x pi upon 2 or negative pi upon 2, and I make y equals 0, these guys are going to be 0. Now, if you go this fella, don't you get x could be 0, and that's the only one that works. And if you take this guy, won't y be pi upon 2, and y could be negative pi upon 2. So now we need to figure out what combinations of these guys and these guys will make both things 0, right? In other words, if I pick this combination of x and y, this will be 0 and that will be 0. Okay, I'll start. If I make x pi upon 2, won't this be 0? If I make x pi upon 2, what do I need to do in the y value to make the second guy 0?
Well, we'll have to be pi halves or negative pi halves.
Okay, are you comfortable how we found those two guys? Now, if I pick negative pi upon 2, won't you also have to do pi halves and negative pi halves? And if I make y 0, right? So if I make y 0, what does x have to be? If I make y 0, what does x have to be to make this 0? If y is 0, what should x be?
The pi halves or the negative pi halves.
Oh, no, this time. Look.
Oh, it will have to be 0.
Right. So do you see in this case, there are actually 5 critical numbers? Are we comfortable with how we found them? Because there's a lot of them. Now, this is where I would stop. Wouldn't I then go and find f of xx and the d value, and depending on what combinations happen, I would end up with a local max, a local min, or some type of saddle point. Are we good with that answer? Or at least as far as that answer goes. So sometimes it's easy to miss one of the potential guys that you could get. Now, although there are 5 answers, I'm looking at the answer here right now. That guy there ends up being the saddle point. 2 of these guys end up being local maximums, and the answer you get in both of them is 8. And 2 of these end up being local minimums, and the answer you get is -8. And when you do local maximum, it's only the values you write down, right? So if you've got 2 local maximums, but they both have a height of 8, you just write 8 in the box. So if you're wondering why, when you go and you do your answer, there is a local max of 8, a local min of 8, and a saddle point 0, 0. That's what your answer would look like when you're finished. Are we good to move on?
Quick question.
Good. I like questions.
Do the constraints actually tell us which octants we're wanting to look in?
Well, we could figure that out. Now, remember, this is the floor of a three-dimensional surface, but we're only interested in the x's and y's. So if you tell me x is between negative pi and pi, you're really saying it's from here to here. And if you're telling me y is between pi and negative pi, it's not so much you're telling me the octant it's in, because it's or quadrant it's in, because a bit of it is in all four. Aren't you really telling me that the answer has to be picked from that box? Right. Now, in some cases, it could be an octant. If I went and said to you, this was your constraint.
Quadrant, there's only four spots on the XY plane.
Right. See, if I told you this is my constraint, if I did that, wouldn't it be 0 to pi, 0 to pi, and you'd be living only points in that quadrant. So in that case, I guess it would be points in the first quadrant. You see? But it doesn't always, right, mean quadrants directly. It depends on the context of the information. Right, good point. Any other questions on these or any of the previous ones before I move on to the next one? Because the next one's the last one of this type. Are we good? Right. Since this is the last one of this type, I think I'll do the whole thing, right? Rather than just get to the bit and say, we would do this, but don't. Of course, I picked a really ugly one, would you agree? We're being asked to find the local max and local min. I don't think this one has a constraint, but let me double check in case it has one and I just missed it. No, this one does not have a constraint. So, partial derivative with respect to x. This contains an x, and so does this. So won't this be, I think, the first product rule that we've needed to do today? And if you differentiate this with respect to x, you basically get 9. And if you differentiate, if you leave this alone, you get that guy. And if you leave the first guy alone, you get that. And if you differentiate this with respect to x, you get e to the negative x squared minus y squared. And it is a chain rule. So what do I finish with? Times what? If you differentiate this expression, you get this expression times what?
Negative 2x.
Okay.
And for the first one, would it be with the 9? Would it be the 9 times the x minus y because the chain rule? Because you're essentially taking out 1.
Well, let me do that on a separate piece of paper to show you what I was doing in my head. I was differentiating this guy, right, with respect to x. I was actually differentiating this guy with respect to x. That's why the answer is just 9.
Okay, so you just distributed the 9.
Yeah, essentially. So I did that in my head, but that's why the 9 is what it is. Now, I'm going to do some style points here. I think I can pull out a 9 and this horrible expression. And that leaves me with a 1 and a negative 2x, x minus y. Yikes. So that's going to be 9, this guy, and a 1, take away a 2x squared plus a 2xy. And that whole, yes.
Is the little chain rule for the e to the negative x squared, negative y squared, is it negative 2x, negative 2xy squared? Because y is like a constant.
Oh, you have, yeah, this is e to the negative x squared plus what? Right, let me show what that would look like on its own.
Oh, it's not times negative
It's not
y
time,
squared.
it's
Oh,
just
I
a,
see.
yeah,
I see.
just
Okay,
a subtraction.
Got it.
So it would be that guy times the derivative of that guy. Right. Oh God, that's horrible. Now, While I've got this one set up, let's try and see if we can find out any kind of restriction on it that would help us. Would you agree 9 is never going to be 0? And would you agree e to this ugly guy is never going to be 0? So I only really need to solve values of x's and y's where that is true. Agreed? That doesn't help the answer become 0, only this term. So that's going to be my equation 1. Now, if I then start all over again, but do it with respect to y, I'm also going to have a product rule. If you differentiate this with respect to y, you will get a -9, not a +9. And then you leave the other guy alone. And then you leave the first guy alone. And you differentiate that, and you get e to the -x² minus y². And because of the chain rule, you get -2y. And in this case, I'm going to pull out a 9, a -ex² take away y² as a common factor. That's going to leave a kind of ugly -1 behind, plus an x minus y times a -2y. And that's going to be a -1, a -2xy plus a y². And since this is equal to 0, and neither of those two terms can ever be 0, we only need to focus on
Should that be 2y²?
which one should be 2y². Here?
Yeah.
Yes. Thank you. So -1, take away 2xy plus 2y². And I'll call that equation 2. So this is, because it's the last one, is kind of keep the best till last. We are trying to solve a system of equations, right? A set of equations with two unknowns, x and y. The first one looks like this. And the second one looks like that. Okay, suggestions. I need to solve it. What you gonna do?
Yeah.
I'll open to suggestions.
Well, I'll just say right off the bat that this will be some pretty nasty algebra.
You would think so, wouldn't you? Agreed? You would think so.
Does that have something to do with the fact that they're equal to each other there?
Interesting. I mean, they are equal to each other because they're both equal to 0. But that's not what I'm going to do. Okay,
Instead of
put out
equal to
your
each
misery.
other and then cancel those ones out.
So
Well, they wouldn't so much cancel, at least not the way they're written right now. But
can't
here's
you
something.
can you reverse the signs on one of them?
Oh, and then make them equal, that would work. I'm just going to do it a slightly different way, but what you said would work perfectly fine. You'd actually end up with what I'm about to end up with. Do you know I can add these two equations together?
Yeah, that'll be solving a system of equations through elimination.
And when I do it, you get that. Would you agree? You get 2y² minus 2x². I'm writing them that way around because it looks better. And can I pull out a common factor of 2? And now that gets me to here. And now I'm going to notice that they are a difference of 2 squares. And you're going to say, well, how will that help me? Here we go. Isn't this one telling me that y has to equal x? Agreed? And if I plug y equals x into either of these two equations, so let's put it into one. So do the restriction or the result that y is the same thing as x and put it into equation 1, what do we now get? We get 1 take away 2x² plus 2x times y, which is x, is equal to 0. And when I put this together, I get 1 equals 0. Conclusion.
There is inconclusive, and one cannot, because one cannot equal 0.
So
is
that one,
impossible.
that's impossible. So that one doesn't generate any feasible solutions. Of course, there is another possibility. Couldn't y be negative x? Agreed? Let's try that one out. If I replace y with negative x again into equation 1, I get 1, take away 2x squared, plus 2 lots of x times negative x equals 0. And that becomes 1, take away 4x squared equals 0. And that becomes 4x squared equals 1. And that becomes x squared is a quarter. And doesn't that give me plus or minus a half? Agreed? And won't y be the negative of whatever x is? So that would make it that way around. Which means that you can have a positive a half with a negative a half y, or a negative a half x with a positive a half y. Do you see we've now found our critical numbers? Sneaky?
But could we also have a positive 1/2 with the, oh no,
Yeah.
because the inverses.
Okay, we're good. So I'm sure there's more algebra ways of coming to the same conclusion, but if you do it properly, that's the conclusion you're going to get. So we now have two critical numbers, and they are 1/2 common negative a half, and the other ones basically switch places. And my f of x that I had a while ago is this horrible thing. And I am now not going to have enough room because I'm looking at this clock and I ain't got enough room to do this, but I'll do the best I can. That's this fella, right? I have still to find that guy. I know what this fella is. We got him a minute ago. He's basically that one there. And I've still to find that guy. Now, once I find this guy, and this guy, won't I evaluate them, say, at that number, and I'll do my test and I'll be able to find if it's a local max, a local min, or a saddle point. And then I could plug in these numbers the second time and find out whether that's the same local max and min. And so I need to find D, which is this fella. As well, okay? And all these answers get evaluated at negative a half, negative a half. And we can then come to our conclusion based on this rule. So I'm going to pretend I know what the answer is. If I wanted to differentiate this again with respect to x, wouldn't I have to call this f and this horrible mess g, and wouldn't I end up doing a product rule?
Yep.
And let's just pretend I know what the heck I'm talking about, and the product rule ends up being -10 when you're finished. It'd be a miracle if it was that nice number, but let's pretend it is. And then I took this guy and I differentiated him with respect to y. Wouldn't I also do a different product rule? And let's say that that guy's -2. And I find this guy and I get 4, just for argument's sake. And you then plug them all into gear and you get D. And D is -10 times 4. Take away 4 squared. And if that was true, because I just made these numbers up, wouldn't actually that be the only guy that mattered?
Would it be -2 squared?
F of xy would be -2
So
squared.
that would be the 2/4 squared.
Right. So the bottom line is it's negative and it would be a saddle point. So can you see that last question? It beat me. I gave enough time, but still didn't have enough time to make it to the end to kind of come to a conclusion. If I started doing the product rule and that, I would need a page of paper and I would already have run out of time. And that's without doing the other missing ones. So can you pretend that's the answers just so you can imagine what the final result is? So since I have a few moments, and not much, let's tell you what's going to happen tomorrow. We're going to be looking at the absolute maximum and minimum of a function, right? Of this kind. Now, Calc 1. If you took a normal function like this, wouldn't that count as the absolute maximum? And since this particular shape travels on forever, wouldn't there be no absolute minimum? So we're looking for absolute max and absolute minimums here. Right? Now, sometimes they will put a constraint on it. In other words, they will tell you you can only use X's and Y's in this region. Right? And that's going to make life a little bit easier because that means that there will be probably an absolute max and an absolute min. The equivalent would be here. Imagine I went and said you started at -3 and you could only finish at 5. Then wouldn't this point here count as my absolute minimum, right? It's the lowest value of the function. And we are going to do the 3-dimensional version of that same thing, right? So can you imagine you've got a surface, right? Isn't there a possibility at least that some point in that surface is higher than any other point in the entire surface's life? That would be an absolute max. So it would be kind of like a point like that, right? If that was the whole shape. If you imagine it, you could have an absolute minimum. Saddle points we don't really care about because saddle points are not going to be max on mins. They're not going to be absolute max and mins, for sure. How do you think we're going to do it? How are we going to find the value of the absolute max and the absolute minimum of a function? I'm probably going to ask you this question tomorrow as well, but right now, how would you do it?
I would assume it would be a similar process with finding the critical numbers.
You're right. And we'll find the critical numbers, but only those that are inside the restricted region, because most of these questions say you can only pick X's in this box, for instance, or only pick X's in this circle, right? That kind of thing, right? But couldn't the absolute max and min be on the edges? So we'll use the critical numbers, you're right, and we'll check them. And we'll also use the boundaries and use them. And if we find something that's bigger on the boundaries or smaller on the boundaries, that's where the absolute max and min could also live. So you check both critical numbers and the boundaries of the shape. And the biggest answer you get is your absolute max, and the smallest you get is your absolute min.